Number 10 on AP9 asks you to find the values of p for which this series converges. In our notes, we said always try the ratio test. Unfortunately, the ratio test does not help us with this one. Let's see what I'm talking about. Using the ratio test, this series converges if this limit of any term divided by its previous term is less than 1. Simplifying and multiplying by the reciprocal of the bottom fraction. 5's cancel out. N plus 4 divided by n plus 3 and n minus 1 to the p over n to the p. We run into a problem. As n approaches infinity, this first ratio approaches 1. But this second ratio, as n approaches infinity, is indeterminable. It's an indeterminate form. As n approaches infinity, we might have 0 over 0, we might have infinity over infinity. It depends on the value of p. It's difficult for us to tell what's happening here. In any case, this is one example where the ratio test does not work. So in that case, what should we do? We are going to do some Algebra 1 skills. Even before algebra, we learned that when we add fractions, you need common denominators. And when you have the common denominators, you can add the numerators over that common denominator. So that 5a's plus 2a's is 5 plus 2a's. Well, think about going backwards. When you have a fraction and the numerator is a sum over the same denominator, we can decompose that into each term over that common denominator and write it as a sum of fractions. That's what's going to happen with this expression. First, we'll factor the 5 out front, and then we'll notice that we have a denominator with two different terms being added, and we will decompose that fraction. So the first term over the denominator plus the second term over the denominator. Now let's distribute the summation to each of these terms. That brings us to this statement, pretty straightforward. And what comes next will be the clever little algebraic trick that maybe you remember should you encounter it on the AP exam. It would be nice if we had the exact same quantity n minus 1 in the top as we do in the bottom. So what if we force the issue? Well, we can't just change things, so we'll have to compensate for that change by doing plus 1. So we haven't really changed anything, it's still just n in the top. But now we'll do the fraction decomposition with this first series. So we have n minus 1 over the denominator plus 1 over that denominator. Again, it might seem a little weird, but if you went backwards, instead if I were adding these two fractions, they have common denominators. So we can rewrite it as one fraction with that denominator and then n minus 1 plus 1 on top. All right, so check this out. We have 1 of these and 3 of these. Now we have 4 of those. And here we'll do the power of exponents when you divide by like bases. So 1 of these and 3 of these is 4 of those, and the exponent here is 1, and therefore we can rewrite the n minus 1 base in the denominator as raised to the power of p minus 1. Remember, p series look like this, and we know that it converges when p is greater than 1 and diverges when p is between 0 and 1, including 1. These aren't quite p series unless you have just a variable raised to the p power, and that variable, that's the base, is the index variable. So we'll just do a little algebraic substitution to write these so that they look exactly like that. Let m equal n minus 1, and then it's going to be exactly in this form. So if m is n minus 1, if we're starting at n equals 2, then m is starting at 2 minus 1, which is 1. All right, well, these are essentially p series now, and they converge when p is greater than 1. In other words, the exponent has to be greater than 1. So each of these exponents must be greater than 1.